Hi, I'm Jordan Goodman. I'm a professor of physics here at the University of Maryland, and I'm going to give you a little virtual tour of the particle astrophysics group and some of the research that we do here at the University of Maryland Department of Physics. So, multi-messenger astronomy is one of the newest and hottest emerging areas of science. For years, astronomers looked at the sky with optical telescopes, and then of course they started using radio and X-rays and even gamma rays, and every area showed new and exciting developments. But the newest field of astrophysics and astronomy is to use different messengers, not just photons, but neutrinos and gravitational waves as well. And so our group at the University of Maryland is one of the leading groups in this new field of multi-messenger astronomy. So let me tell you a little bit about the particle astrophysics group. Well, what particle astrophysics studies is it's got connections to astronomy, cosmology, high energy physics, and nuclear physics. And we study cosmic rays, dark matter, neutrinos, and of course, multi-messenger astronomy. Now, at the University of Maryland, one of the things that positions us so well to do this is we have really strong groups in working on, for example, IceCube, and the radio extension of it, which is Greg Sullivan, Kara Hoffman, and Eric Blaufus. And then Andy Smith and I work on the high energy gamma ray experiment, HAWK. And we have associated groups with Peter Shawn working on gravitational waves and Carter Hall working on dark matter. We're also part of the Joint Space Sciences Institute, which is an institute that brings together scientists from our groups at Maryland in the physics department and astronomy department, as well as people from the Goddard Space Flight Center to work together on common topics. And Goddard is about 3.5 miles away from Maryland, and makes it a very good opportunity to work with us on, and our students have opportunities there as well. So, just a talk on this stuff sort of begins with one of the most interesting things that we look for is to understand where the highest energy particles in the universe come from. So this graph you see looks like a straight line, which may or may not be so exciting until you realize what it is. It's the flux of cosmic rays as measured over 12 orders of magnitude in energy and 32 orders of magnitude in flux. And what we've known for almost 100 years is that really high energy particles impinge upon the Earth. And we've known for quite a few years that some of them go to extraordinary high energies, like 10 to the 20th electron volts, a factor of 10 to the 7th higher than you can get at the Large Hadron Collider. And what we're trying to understand is how do you produce these extraordinary high energy particles in space, and what are the objects that produce them? So why don't we just look up in the sky and see where they come from? Well, the problem is they're charged cosmic rays. And charged particles are bent in the magnetic field of our galaxy and in the local cluster. So if this is the map of the galaxy, and here's College Park, and we see a cosmic ray coming toward us, we don't know that it's not, we do know that it isn't pointing back to the direction it came from because it's been bent by the magnetic fields. And to get high enough energy so things point, it has to be significantly higher than even 10 to the 19th electron volts. So the way around this is to use neutral messengers that point back into space. Now, for energies below about 10 to the 14th electron volts, gamma rays are a plentiful subject which are relatively easy to detect and can point straight and move in straight lines and can point straight back. Above that, the universe starts to become opaque through pair production. A gamma ray can interact with the extragalactic background light and produce an electron-positron pair and is lost. But at the highest energies, the best way to look for the exotic objects is to use neutrinos. And so our IceCube experiment is one of the ones that can look at the first to discover extragalactic neutrinos. So what could produce such a high energy? Well, if you think about the Large Hadron Collider on Earth, the thing that restricts its energy is the product of its magnetic field and the radius. So if you build a much larger machine, you can accelerate things higher, but the cost goes up to become prohibitive. In space, it's that same product of magnetic field and air and radius that sets the maximum scale for energy. So if you're interested in producing a 10 to the 20 eV electron, and you have, for example, a field of 2 Tesla, you need a radius which is the radius of 1 AU. So you'd have to build an accelerator that traces the Earth's path around the sun. So we look to try to understand what are these exotic objects that have this intense magnetic fields and these large areas, and things like active galaxies and gamma ray bursts are things that are obvious targets, and we're just now beginning to see that some of these are producing the highest energy particles. So I mentioned active galaxies. So at the center of most galaxies is a supermassive black hole. And as material accretes into this black hole, jets of particles and high energy plasma move out of this thing, and in these jets that move out from the top and the bottom of the galaxy. And in these jets, there are plasma shocks that move through each other and accelerate particles. And what we know is that when these things point at us, an object called a blazar, that we see extremely high energy gamma rays, and now just recently we've discovered that we've also seen evidence of high energy neutrino emission from these things. To give you a scale, here's an actual photo of one of these things, not an artist's conception, taken with the Hubble telescope, and you can see the jet being 5,000 light years long. Gamma ray bursts are some of the most energetic phenomena in the universe. About twice a day, something goes bang somewhere in the universe that produces more gamma rays than the rest of the universe combined. And what we now know by, again, using multi-messenger astronomy is that's at least gamma ray bursts can be produced by merging binary neutron stars. And this was a discovery made in the last couple of years using the LIGO experiment and the Fermi Gamma Ray Space Telescope. I work mostly on the HAWK experiment, which is the High Altitude Water Cherenkov Observatory. Here's a picture of the HAWK detector in the high mountains of Mexico. We're at an altitude of almost 14,000 feet. Each of these is a giant water detector that's used to detect particles coming down from cosmic rays in the atmosphere. If I blow it up a little bit, you can see HAWK has 300 of these giant tanks, each 50,000 gallons of water. And to give you some scale, there's a person walking along to see how big these things are. So it's a giant detector, and when the particles hit the detector, they produce light, and the particles move almost in a plane, moving at the speed of light as they come down, pointing back to the direction they came from. And we can use this to make maps of the sky in the highest energy gamma rays. So here is the most recent map from the HAWK data showing the center line of this is the galaxy, our galaxy. The big holes are the areas we can't see from the northern hemisphere we are, so it's the southern hemisphere and the very north pole. But what we see is extremely high energy gamma ray emission from an enormous number of objects, many of which we with HAWK have discovered for the first time. So we map out these galaxies and we study the properties of the individual objects that produce them. And this has been really exciting. We've also been able to make the highest energy map of these things to look up to 50 and 100 TeV view of the sky. And we see that some of these objects, which are extended objects, are still glowing at between 50 and 100 TeV of energy. So this is kind of exciting, and we can start to study the acceleration processes and map these objects out. One of the things that we've also seen is something called a microquasar. What a microquasar is kind of like one of those big AGN, but in our galaxy. It's like a model of it. Instead of having a giant black hole, you have a stellar mass black hole and a companion star that feeds it, and it has jets. And what HAWK discovered for the first time was that these jets could accelerate tens of TeV or 100 TeV particle to produce tens of TeV photons that we detected. And this is really exciting and one of the things we're studying. We also look for transients when some of these active galaxies flare. Here's a picture of the Markarian 501 flaring a couple years ago. And HAWK notifies the rest of the community when this happens because we look every day, 24 hours a day at the whole sky. Now, one of the most exciting things that's happened recently has been gravitational waves. So far there have only been 2 binary neutron stars detected, but a whole lot of merging black holes. And what we would like to do is to be able to look if there's a binary neutron star merger in our field of view to see if they produce really, really high energy gamma rays. So this circle here represents where is the HAWK field of view, and the red line is the LIGO contour for, in this case, it was a black hole merger, but that where they define the trajectory across the field of view. So we look on various time scales, and we've yet to find a coincidence, but this is something that's reasonable to expect over the next few years. Our group also works on, and I have worked on in the past, IceCube. An IceCube is a cubic kilometer detector buried in the ice underneath the geographic South Pole. Now, to give you some scale of this, the color picture on the right is the Super Kamiokande detector, which I worked on buried in a mountain in Japan. And you can see 3 guys in a boat servicing. It's an enormous detector. But this picture shows you that this little black dot in the middle here would be the size of the Super K detector on the IceCube detector, which is a cubic kilometer, a gigaton of ice. And the IceCube detector has detected for the first time astrophysical neutrinos coming from extraterrestrial sources. And they're using this detector to point back into space. And one of the most exciting discoveries was that they saw one of these really high energy neutrino in coincidence with a flaring AGN. So the fact that the gamma ray telescopes could say it was flaring and they saw this neutrino is another example of multi-messenger astronomy. So in conclusion, let me just say that multi-messenger astronomy is one of the top emerging areas of astronomy and astrophysics, and Maryland is one of the best places to study this field. We have incredibly strong groups in HAWC, IceCube, and LIGO. We have strong ties to the Maryland Astronomy Department. We have opportunities for research at the Goddard Space Flight Center, and Maryland's just a great place to come to graduate school. So I'm here to welcome you to our virtual open house, and just put my information back up there again, goodman@umd.edu, and I'm happy to communicate or talk with any of you. So thank you and have a good open house.